Okay, yeah. I don't want to break anything. Yeah. All right, it's 10 past, so we'll get started. So I'd like to welcome everyone back to our fifth and final lecture in this year's Nobel Lecture Series, which is titled The Role of Turbulence in Oceans, Atmosphere, and Climate. So it's my pleasure to once again welcome our speaker for this year, Professor Raffaele Ferrari. As my colleagues have highlighted in previous introductions, Professor Ferrari is an extremely accomplished researcher, and he's received a vast number of awards for his research over the years. One such award is the Ally of Nature Award, which he received in 2019 for his work on developing new generation climate models, which we saw in his presentation yesterday. Over the past 25 years, his research has spanned a broad number of topics, including atmosphere dynamics, ocean dynamics and modeling, as well as biogeochemistry. In addition to expanding our knowledge on the climate and environment of the Anthropocene, he's also worked on the paleoclimate as well, in particular, the last glacial maximum, as well as the Eocene period. So in today's talk, he's going to take us on a trip back in time to learn about the role that oceans have played in the last ice age. So with that, I'd like everyone to join me in welcoming Professor Ferrari once more.
Thank you. Yeah, thank you. And thank you for sticking with me for 5 days. Some in presence, some not. But we are concluding in presence, which is a good sign. And what I'm going to talk about today, indeed, is, in some part it's different from what we've been talking until now, in the sense that we're trying to look at a different mean climate state and the role that the ocean might have played in that different climate state, but in some ways it's still connected to what we have been talking the last few days, because I will, maybe you might expect that turbulence in the ocean will play an important role in what I'm describing, or at least I'll contend that understanding a bit how rearrangement of ocean circulations in different climate occurs has also to do with rearrangement of the turbulence in the ocean itself. And what I want to talk about in particular is the last ice ages in general, and in particular the data from the last glacial maximum, so connect and understand what happened when the climate of the Earth got much colder than today. This is just a simple depiction. You shouldn't take it too seriously, but just to show that clearly the climate was much colder 20,000 years ago. There were a lot of land ice. Dick, who cannot be with us, Dick Peltier, is definitely an expert on reconstruction of the sea ice, on the land ice distribution. Since the climate was colder, there wasn't just more land ice, but also sea ice. The sea ice extent was probably more vast. We discussed that in a bit more detail. But what we want to understand is that climate got colder. The temperature of the ocean dropped by about 3 degrees C. The surface temperature where it was more amplified at the poles. But temperature got very cold. And we want to understand what allowed the climate to plunge in such a cold state. And when I say that the climate got colder, we do actually have direct records of temperature changes. So this is from a Vostok ice core. So you drill a core in the ice records past air information, or there are bubbles of past air that have remained trapped in the ice. And so you can reconstruct how the air stored in those bubbles have changed in its composition over time. And so now you're seeing, as a function of time, you go from the right to from the left to the right. That's always a bit of a problem for me, for paleo data that like to have the axis in time going backwards, but we can live with that. What you see is that this is over the last 4 glacial cycles, over 400,000 years, pretty much. You see 2 curves. One is the temperature in red. The temperature is recorded from isotope of oxygen. You don't have to go into the details, but you just see that you can, these bubbles records a bit the change in temperature, a leading order over time. And so you see excursion of about 10 degrees C. This is at a very high latitude, so it's the largest temperature swings that you're going to see because it was the temperature at high latitude. Now, one of the challenges is that that temperature increase can't really be easily explained if you just look at changes in orbital forcing on the planet. Yes, the change of the orbits had less insolation at high latitudes in the northern hemisphere, but by itself, it would have supposedly, from what we understand about the climate system, should have contributed a much smaller temperature difference than what you see in that picture. However, there is a second hint of what might have precipitated that temperature increase is the second curve, the blue one, which is swings in carbon dioxide concentration in the atmosphere. That is directly stored in these air bubbles. And you see that carbon dioxide concentration are also swinging back and forth. There is much more carbon dioxide in the atmosphere when you have warm climates. These are these peaks that we see in the picture. These are what calls the interglacial periods like the Holocene we are living in. Carbon dioxide concentration at that point was of the order of 280 ppm, parts per million. While when you are in these cold climate states, the carbon dioxide concentration are nearly 100 to 90 ppm lower than during this interglacial period. So the carbon dioxide concentration really dropped in the atmosphere. We know that carbon dioxide is a very strong greenhouse gas. And so the understanding is that that swing in carbon dioxide is what amplified the change in radiative forcing and really allowed the temperature to drop as much as we've seen. So now the question is, well, okay, so the carbon dioxide in the atmosphere dropped dramatically. Where did that carbon go? Because it still had to be in the climate system. In a sense, you know that there are only two pools of carbon that are easily movable in the climate system. One is the carbon stored on land, and the other one is the carbon stored in the ocean. On land, as far as we understand, the climate at the last glacial maximum was such that there was much less vegetation. So if anything, the land became a source of carbon dioxide because you were losing a lot of the carbon stored on land today for a number of reasons, possibly just because of the decrease in CO2. Plants are less efficient at growing. Maybe it was a more arid climate. It's possible that was also cause. In any case, it doesn't seem that land would be an easy way to store carbon. So the next obvious candidate is the ocean. So the question here we want to address is, why would the ocean be more effective at storing large amounts of carbon during a glacial climate? And if we look at the ocean, do we see any signature that the ocean had transitioned to a different state in a glacial climate? And this is a picture of delta C13 as reconstructed by Curry and Oppo by taking vertical section in the ocean. Well, what they do is that they look at foraminifera, benthic foraminifera that store carbon when they grow their shells, and they record the value of delta C13 at that time. For the moment, delta C13, you can consider it as some funny dye that enters into the ocean, so it doesn't matter what it really records. But as a dye, you can see now I have two maps. They're both from the Western Atlantic, and the vertical axis is depth, and the horizontal axis is latitude. On the left panel, you're seeing the delta C13 distribution for the present day, or technically the pre-industrial value. We unfortunately have flooded with delta C13 by emission of greenhouse gases in the atmosphere. Now there is a new signal coming in, but these are records from the past. So we're trying to look at what happens before we have the strong signal coming from the surface. And what you see is a picture that at this point should look pretty familiar, because we're looking at the North Atlantic, and you see this big tongue of high value in delta C13. But those are really recording. It's waters that were formed in the North Atlantic and through convection are sinking into the ocean interior. That's the picture we've seen in the first couple of lectures. There is convection in the North Atlantic. You have a source of dense water, and that's that signal that is carrying that signature of high delta C13 in the North Atlantic into the interior of the ocean. Instead, there is a much lighter source from the southern hemisphere that sinks below it. And this is convection around Antarctica, bringing waters towards the north. So those were the two sources that we described in the first couple of lectures. Indeed, if you look at the picture of salinity in the present day ocean, it doesn't look terribly different from that because it's recording the same patterns. And that's a picture that we've seen in the first lecture. Now, if we look at the same picture, but now for a slice that was taken 20,000 years ago, so again, by looking at this benthic foraminifera, you can track and look at delta C13 at different times, because you can time when that signal was stored, how old that particular foraminifera is. You get the picture on the right. The first thing you see by eye is that it's very different from the one on the left. So at least the ocean distribution of that dye seems to be different. In particular, it would seem to suggest that if I look at it, that the amount of water mass that was coming from the southern hemisphere has expanded quite dramatically compared to what it was in the left panel. So there is more southern waters that is formed through convection around Antarctica that fills the deep ocean, nearly up to 2,000 meters, where in the present day climate, it wasn't getting above 4,000 meters, it was much deeper down. And the source of water from the North Atlantic seems to be trapped all above 2,000 meters, while in the present day ocean, it was getting down to nearly 4,000 meters. So this has been, it looks like there might have been a shift or rearrangement of water masses. That starts being a hint from the seminal work of Curry and Oppo that, yeah, maybe the ocean mean state was very different. And now the question is that an effective way to store carbon, that new configuration is that suggested way forward for carbon to be trapped into the ocean. So now we step back. This is the context. And we want to look at what would we expect an ocean to look like, or how do we expect an ocean to change between the present day climate versus a glacial climate. We're going to take it at a very basic level. And in order to understand that, we have to first understand what sets what we think is the basic structure of water masses in the present day ocean. And then we discuss how it might change in a colder climate. And I'll try, or at least the position we'll take, or the hypothesis we want to test, is how much expansion of sea ice might have played a role in that rearrangement. And I always like to say that if they're called ice ages, probably ice should play a role in it. So let's start looking at the structure of the ocean today. The panel again is showing a figure that we've already looked at a few times over the last few lectures. It's again as a function of depth and latitude, and I'm looking at the density distribution of the global ocean. Right? So light water on top and dense water on the bottom. Sorry that light is blue and dense is red, maybe you like the opposite signature, but blue here means light. And the basic picture that you see, we already discussed it, is if you look below 1,000 meters or so, and I'm insisting below 1,000 meters for two reasons. First of all, you've seen this big rearrangement of water masses is something we've seen happening at depth in the ocean, not necessarily at the surface. It's also that we see that carbon is likely to be stored at depth in the ocean, not toward the surface. I guess in one of the first lectures, we've seen that the amount of carbon or distribution of carbon had to be bottom intensified in the ocean. So that's where you store most of the carbon. So it's really the deep ocean that might have played that role. So if we look below 1,000 meters or so, you see density surface north of 50 degrees north or so. So north of the Southern Ocean, they're pretty flat. Okay, so that seems a pretty easy statement. As the surface don't tilt much. They tilt a lot in the North Atlantic. We know that that part, north of 60 degrees north, there is only North Atlantic waters. The Bering Strait closes the Pacific. But those are vertical just because of convection in the North Atlantic. So we understand what that is. But the other part that is interesting is the Southern Ocean that has this very steep sloping isopycnums, right? Here, there, the isopycnums are clearly not flat anymore. And we want to understand what sets that pattern, because we see that that's crucial to understand the overall structure of deep water masses. So first, let's focus on the Southern Ocean and see what sets that structure. Well, we now discussed a few times that what is happening in the Southern Ocean, you have these strong winds, the westerlies blowing over the Southern Ocean. They are coming at me in a rotating planet. A westerly wind coming at me in the Southern Hemisphere is going to drive a current to the left of the wind. So there is an Ekman flow coming from left to right. In order to close the budget, it means that there is water that is brought to the surface along Antarctica to feed this Ekman flow. And then since the wind slacken down, and so the transport, the horizontal Ekman transport comes down, then there must be a flow of that water that was pushed northward has to come down. So the winds are generating a clockwise circulation. So if you think starting with flat isopycna, we described in the last few classes, in the last few lectures, you tilt isopycnas from the horizontal to the vertical. If only winds were acting, the isopycnas would become straight vertical. Indeed, the first very coarse erosion climate model ended up in this funny state where isopigment Southern Ocean were getting straight. So now why is it that they don't get straight in the real Southern Ocean? Well, this was the topic of what was the 2 lectures ago. Baroclinic instability kicks in because you start steepening isopycnal more and more, you generated a stronger and stronger lateral density gradient here, down density. If you started from flat where there was 0 gradient, but now you're tipping isopycnal, the gradient is increasing. A lateral density gradient means that there is in thermal wind a very strong zonal velocity. The ACC eventually goes unstable and starts flattening the isopycnal until to reach an equilibrium. And just in the context, early climate models were very coarse. They didn't resolve baroclinic instability, but they didn't parameterize it either. So as a result, they were getting this funny state of vertical isopycnals. So Jentem-McWilliams, that people might have heard of, is a closure for baroclinic instability, deserves a lot of credit in the ocean community. The main point they made was how do you represent this qualitatively, this effect of eddies trying to resist the effect of waves, and that made a big push forward in ocean modeling, that otherwise you had ocean models that were hard to present in front of an observational audience that would just laugh at you when they look at the structure and say, well, that's not an ocean, it's something else. So that is important because then if you want to know what is the slope of those density surfaces, is essentially given by a ratio of the strength of the wind, tau, and well, divided by density of seawater and F. Those are just external parameters that are fixed in any climate. We don't think that the spin of the Earth really changed much or its density, but it's divided by this eddy diffusivity kappa, the diffusivity we talked about in the previous lecture, which represents the strength of baroclinic instability. So up to this point, all I'm saying is that the slope is proportional to the wind stress. Well, the larger the wind stress, the steeper the isopycnal, but then it's inversely proportional to the strength of baroclinic instability that resists it. So the stronger the baroclinic instability, the weaker the slope, and the two eventually reach. It's essentially a tug of war until they reach an equilibrium, which is given by that ratio, right? So winds and eddies are what sets the slope of those isopycnals. So now, in a sense, if you know what is the slope of the isopycnal, you've done most of the work in understanding the structure of the deep ocean, because you can infer what is the density distribution at the surface north of the ice line. Density is essentially restored to the surface temperature, or maybe salinity changes a bit the picture, but you know essentially what is the distribution of density at the surface. Now, if you know the slope, you just, even by that ratio, you know winds and the eddy strength, you follow that slope. Indeed, if you put values of present day wind stress and eddy diffusivity, you get a value that is close to 10 to the minus 3 for your typical slope, and that is the dashed line that I'm drawing. You see that it matches pretty well what the data suggests. So I can just, given the surface value that I know because of the property in the atmosphere, I follow the slope up to the Southern Ocean, and then once I hit the Southern Ocean, as I said, it's a flat density surface. Essentially, I reconstructed based on surface information the density structure in the interior of the ocean everywhere. That's a simple way to describe what sets the deep stratification of the ocean. Is this tug of war between wind and eddies in the Southern Ocean that set that slope, and then I can just propagate that forward. So now this tells me a lot about the stratification. I also want to know about the circulation itself. So how do I derive a simple story for what the circulation of the Southern Ocean, of the global ocean, should be, just based on simple thermodynamic argument based on the fact that I now have a simple story for the stratification. To understand that, I can start by looking at the surface fluxes, now buoyancy fluxes, at the surface of the ocean, where the ocean is being made denser or lighter by the atmosphere. And you see this picture here where it's red, it means that you have positive buoyancy fluxes, and when it's blue, it means negative buoyancy fluxes. We see that very close to Antarctica, you have very strong negative buoyancy fluxes. These are mostly due to brine rejection and cooling under sea ice. You see maybe these two white lines. These are some estimates of the permanent sea ice. And what I mean by permanent sea ice in those two lines, I think they are the isolines of when the ice is present, something close to, well, I think the upper line is something close to 70% of the time. And so that means that below the white line, standing further out, 70% of the time you have sea ice. The other one is an even higher threshold, this lower one, maybe it's 80% or something like that. So what it shows is that if you are, when you're under sea ice, water is getting denser. As you form new sea ice, you release some of the salt that was in the water that you form, and so that generates very dense water. As soon as you move north of that permanent sea ice line, this is the permanent, so it's the sea ice line essentially you're expecting summer because it's as the system has retreated and warmed up. North of it, instead, you have strong buoyancy fluxes. Here I just say that there is atmospheric heating in summer, but there is also large contribution from precipitation, both of which make waters lighter. So now you have a very strong band, a very light or positive buoyancy fluxes. If you go further north, then things change again because of evaporation and other effects. That doesn't matter too much for us, at least in this discussion. So I guess the point to take home here is that there is a shift between negative and positive buoyancy fluxes pretty much at the permanent sea ice line in present climate. Now that can help us to understand what the circulation of that system has to be, because now I'm drawing us just a portion of the Southern Ocean of our stratification estimate, and now I'm putting some permanent sea ice at the top, just to remind ourselves there is some region which is mostly covered by sea ice around Antarctica. And now the dashed line is one particular density surface, is the one that outcrops at the surface just at the edge of the sea ice line. So I say, well, I know what the temperature is there. Then I can follow the density surface because I know the slope, and then it flattens out, right? What I said before. Now think about waters that we said are brought towards the surface by this wind divergence, right? The wind creates a divergence and just brings water towards the surface. Now, what happens when this water comes at the surface? Well, water that comes at the surface below that dashed line, that particular density surface, when they come to the surface, they are exposed to buoyancy loss, right? They're coming at the surface in a region where the water is made denser by the fact that you're generating new sea ice at the surface. Now, if you're getting denser, that water has to move southward because as it's made denser, it's moving towards colder waters, which are to the south of it, right? This is just a thermodynamic argument. I have water that goes from dense to light at the surface. Coming at the surface, there are a negative buoyancy flux, so it moves south just to move towards heavier and heavier density, right? That water is getting denser, it's moving towards the density, the cold density classes. However, water that outcrops at the surface above the dashed line is exposed to a positive buoyancy flux. So that water, as it comes to the surface, is made lighter, so it has to move north towards lighter waters because it's made lighter, right? So just a thermodynamic argument, you're just saying you come to the surface, so you must have two cells, one that moves waters towards lighter density surface and one towards denser density surface, and that separation happened at the permanent sea ice line because that's when the surface heat flux is really changing sign. So now, does that bear some resemblance to the global ocean circulation? I would contend actually it does. Now we're looking and we're trying to understand the full overturning circulation within this framework in mind. Now this is diagnosed from real data. So we have the overturning in the Atlantic, in the Indo-Pacific, and in the Southern Ocean. And the vertical axis now is densities instead of being depth. It's easier to plot properties in terms of density because especially the Southern Ocean protein moves essentially along constant density surfaces. And the horizontal latitude instead this is the Pacific, so they all start from 32 degrees south all the way to the Northern Hemisphere, while from 32 degrees south and south, we take a zonal average over the full Southern Ocean, right? South of 32 degrees south, there is just one big ocean. You cannot take average only over a sector, while north of it, it's an average only on the Pacific and average only in longitude over the Atlantic. So first of all, if we look at the Southern Ocean in that picture, there is again that dashed line that supposedly represents the density surface that outcrops the sea ice line. And you do indeed get two overturning circulation in the same sign. What I described, this is water that outcrop at the surface. Now the surface, since we're looking in density space, is somewhere down here because the surface change, the density changes along the surface. So your surface is somewhere cutting along a line like this here. So you see water that outcrop under the sea ice line, they get denser and they come back. And the water that instead outcrop at the surface above the sea ice line go around this red line, which means that they're undergoing a clockwise circulation. These are streamlines. And so the waters above the sea ice line indeed are moved towards lighter density and come back, right? So the Southern Ocean picture is exactly what I tried to depict in the simple schematic. Now let's see how the two other oceans, the Atlantic and the Pacific, connect to that picture. in the present day climate. So in the Atlantic, we see now again, these lines are ice stream lines, the lines that water muscles follow on average. So you have sinking at high latitude. This is convection. This water moves all the way south to the Southern Ocean. And by the time they arrive to the Southern Ocean, they have density around 1,028 kilogram per meter cube. So water that dense, if I look here, right, they are definitely below 27.88 if you want, which is a bit the density surface is separating these two pathways. So what it means is that these waters essentially enter in the Southern Ocean, and they're dense enough that they mostly outcrop under permanent sea ice. If they outcrop permanently under sea ice, well, they are transforming even denser water in the Southern Ocean, then they flood and mostly flood the Pacific, also a bit in the Atlantic, but mostly in the Pacific. So this water sinks at depth in the Pacific. So all this water that were formed through convection in the North Atlantic ended up as even denser water in the Pacific. Now, this water in the Pacific finally are experiencing, spend a lot of time there, and they have time to experience a lot of diffusion. This was the overturning circulation we described in the first lecture, this abyssal circulation. Now, mixing is lifting this water up pretty much to the depth of the ridges and seamounts in the global ocean, right? This is where mixing is most intensified, because mixing is intensified where there is topography. And so this water comes towards the surface up to close to 2,000 meters or so. And this is, again, these black and gray lines are the typical height of topographic features in the Indo-Pacific basin. I think the gray one is the Indian and the black one is the Pacific height of topographic features. And you see that this water, by the time they come back because of diffusion, they have gotten as light as about 27.88, maybe 27.6. Once they come to the Southern Ocean, they are light enough that they are above this density surface that separate the two cells in the Southern Ocean. This density surfaces are cropped at the sea ice line. So they are light enough that they get transformed in lighter water, and finally they flow back into the Atlantic. Maybe I can show this is in an even simpler schematic just to show, and the point I'm trying to make is here is if you're looking at zonally average sense, the two loops in the Pacific and the Atlantic, they're really strongly connected today. And the reason why they're connected is that mixing is able to convert very dense water to water that are light enough that by the time they come in the Southern Ocean, they can be transforming lighter water but go back in the North Atlantic. So again, this is the same schematic, just to repeat the story. And the reason I'm repeating it twice is it's going to play an important role in understanding how things change when we go in a glacial climate. We have water sinking at high latitudes. They flow all the way to the Southern Ocean where the winds bring them to the surface. The Southern Ocean is the only place where wind divergence is strong enough to really bring deep waters all the way to the surface. You don't have a strong divergence anywhere else in the ocean, really. So waters come to the surface, but they are so dense that I end up outcropping under the permanent sea ice line. So they're transforming even denser water in the Southern Hemisphere. They flood in the deep Pacific and part in the deep Atlantic. And now diffusion brings them up all the way pretty much to the depth of mid-Atlantic ridges and seamounts, because that's where mixing is intensified. That's where it can bring you up. Once this water come back to the surface, when they arrive in the Southern Ocean, they're light enough that they can be, they outcrop north of the sea ice line and they can come back all the way to the North Atlantic. So that's the state of the climate today. This is a picture that, you know, this particular picture was inspired by Lynn Talley. Maybe I should have pointed out that all the dynamics of the Southern Ocean work that was done by John Marshall at MIT, Paola Cesi and Chris Wolf, Max Nikorash and Jeff Vallis have contributed a lot to these ideas. So that's something that most oceanographers would agree on up to this point. Now, what happens when you go into a glacial climate? Well, the first thing that we know is that the climate gets colder. That's what the glacial climate is. And for the moment, I'm not talking about how do I enter into a glacial climate. I'm just trying to understand what is that new climate that we call the ice climate. So we just want to get a new picture equivalent to the present day now for a climate that was as cold as the last glacial maximum. So here now we are looking at model output. This is CCSM3. It's a model run at NCAR that is being forced with colder temperature, or essentially lower greenhouse gases, and let it equilibrate. The upper picture is instead the present day, so the same climate model, but forced with present day greenhouse gas concentrations. I think in the two models, they also changed the distribution of land ice based on reconstruction, like the one of Pic Pelletier. So what you see before, again, in the present day climate, they get a very thin layer of negative buoyancy fluxes that is well tracked by the permanent sea ice line, which is now, again, these two white lines are two slightly different definition of the permanent sea ice line. If you look closely, you also see a dashed white line. That's the -2 degrees C isoline in this atmospheric temperature. Why I choose that -2 degrees C? Well, that's the temperature at which the salty seawater freezes. It's just telling me, well, the permanent sea ice line is essentially at the location of the -2 degrees C isoline in summer, right? Because I want the permanent sea ice. That temperature never goes above freezing over the whole year, so the water is always frozen. It's not a particularly subtle thermodynamical statement, right? If you have a place in the ocean, well, if it was fresh water, you would look for the zero sea ice line, for the zero air temperature line in the ocean, you look at the -2 degrees C. So now let's look at what happens when we enter into this other simulation, which is a glacial simulation. It's a colder climate. Now the negative buoyancy fluxes has expanded. And indeed, if you look at the white lines, this is again to slightly different definition of permanent sea ice, when sea ice is permanent more than 70% of the time. And that tracks pretty well this separation between the negative and the positive buoyancy fluxes. And if I look at the dashed line, the -2 degrees C temperature isoline, also that tracks. So indeed, it's just that the climate got colder, so the -2 degrees C temperature isoline must have moved northward away from the poles because the climate is quite a bit colder. So you would expect an expansion of the permanent sea ice coming together with that. So now, if we believe that, which seems a pretty simple thermodynamic argument, and there are some radiolarians that are evidence, at least in part of the Weddell Sea nowadays, emerging that the sea ice did definitely expand, and they just can see by how much production there was in summer versus not. So you see north of which lines you actually have strong production, because you need to have free water at some point for light to penetrate and have substantial production. So there is some evidence from very indirect proxies that the sea ice line have expanded, but I would contend that this is one of those examples that you need to think about very creative way in which that would not happen, because you're getting a colder climate. So you already have some permanent sea ice. How would you avoid generating it? Maybe there are ways, but this seems a pretty robust inference. So if we believe that, how would that impact the circulation of our ocean? Again, we go back to the present day ocean where we had some permanent sea ice, and we know that there is a slope S of isopycnal. So if I want to know how deep that isopycnal sinks, the isopycnal that accompany the sea ice line, how deep does it penetrate in the ocean interior? Well, H, the depth to which it penetrates, is given by the slope of the isopycnal times L, which is the distance between the sea ice line and the edge of the Southern Ocean, right? Because the slope S is just given by H over L. It's a triangle, right? So if I know that, how would that picture change if I move in a glacial climate where the sea ice has expanded? Well, when the sea ice expands, the first thing that would definitely change is that L, the distance between the sea ice line and the edge of the Southern Ocean, has shrunk. Now, for a moment, let's assume that the slope doesn't change. If the slope doesn't change, that's because that L has decreased. You can predict that your density surface that occupies sea ice line in most of the ocean basin has moved upward, right? And you can even infer that it turns out that the sea ice line might have expanded by 5 degrees or so, and that will correspond to an expansion of the sea ice line, an expansion of the sea ice line by 500 kilometers or so, and that would correspond to a shoaling of the density surface by order 500 meters or so, just to give some number. So it gets quite a bit shallower, just in response of the expansion of the sea ice. So now that would have a profound impact, we contend, on the overturning circulation of the ocean. Again, the upper picture is the present day overturning. Now, the lower picture is trying to reconstruct what would have happened in a glacial maximum. Now, you see that in the present day, that density surface that was outcropping and the sea ice edge is essentially sitting very close to the edge of, very close to the typical height of mid-Atlantic ridges and seamount. So the ocean or mixing is barely able to get waters light enough, as we said, that when they come to the surface, they can be recirculated and pushed to the North Atlantic. As soon as you lift that lid by another 500 meters, your density surface now is sitting mostly above mid-Atlantic seamount and ridges. By the way, this is something we've seen in the proxy data. It really looked like this deep water that we were seeing in the Delta C13 were expanding upward, right? So that there is already, and we'll come back to it, some evidence that that is something we've seen. So now how does the ocean circulation in this new configuration look like? Well, now we can really think about what happens if we start from the previous solution. Now the sea ice line has expanded, the density surface has lifted. Now you have water sinking from the North Atlantic. At the beginning, they are still sinking deep enough. They come all the way to the Southern Ocean. They are transformed to dense water in the Southern Ocean. They sink into the Pacific. That mixing is lifting them up. But by the time they get to the surface, they are still outcropping under the sea ice line. Now they don't go above the sea ice line. And so they start recirculating in the abyss. Sorry, this will go on for a while until essentially you have a new configuration where there is this water below that density surface, which is always trapped below the density surface because it has no way to ever become light enough. Mixing is not lifting it enough to cross that density surface. And then you're going to have a shallower overturning, mostly confined to the North Atlantic, that just sits on top of that because the two cannot exchange anymore. The only reason why you have this interconnection today is because there is enough mixing that keeps them connected. But if mixing instead, or the density surface is shallower than where mixing is intense, then it cannot connect the two loops anymore. Now that starts suggesting, yes, there might have been a very large change. That is what happened. And indeed, this circulation now seems to never outcrop except under permanent sea ice line, which is a very good way if you start thinking, and we'll get there, that if you want to store properties in the deep ocean, well, never allowing the ocean to come to the surface and be exposed to RC fluxes is a good way to store whatever you want for a much longer time. Before we address that, however, we have to spend a second to discuss this question: did the slope of the density surface change? Because I tried to make the statement, well, you just shift. The reason why I was claiming there was a shoaling of the density surface was because I kept the slope constant. Of course, if the slope had increased there, well, then that argument might not hold. So we want to know what could cause a change in that depth h. The depth of that red line is given by the product of the slopes times L. That's what we wrote before. And for the moment, just allow L to change, but let's see how S could change. And so given that that's just the product of two functions, I can look at what is the ratio of delta H over H, the rate of change of H divided by H, because if I write it that way, well, that is given by the fractional change of delta S over S, the fractional change of delta L over L. So it's the sum of the changes in slope plus the sum of the changes in L, as long as the two are small, right? So what can make S change? Well, we said that S is, the slope is really set by the winds and the baroclinic eddies that try to slant. Winds that tend to make the density surface steeper, and the baroclinic instability tends to make it lighter. Again, since S is just the ratio of two functions, its fractional change is then proportional to the wind stress change minus the change in the strength of the baroclinic instability. Right? So it's that difference, and then there is the change of delta L over L. Now, it turns out that the winds, the strength of the winds, that has been the focus of quite a bit of literature on how much it could have affected the Southern Ocean structure and affected the glacial climate. Well, you might have changed by some fraction up to maybe 10, 15%, 20%. The problem is that as soon as you increase the winds, this is the part that had not been appreciated early on in the work, you're making your current much stronger and therefore more baroclinically unstable, and the winds or the diffusivity or the strength of the baroclinic instability is increasing proportional to it and tries to react, right? Because indeed, you're providing more energy for the instability to grow as well. This is something that in the atmosphere is pretty well recognized. There are ideas that are called marginal criticality, where the whole atmosphere and the slope of isentrope in the atmosphere is set by a balance, in that case, based on thermodynamic forcing, radiation, and baroclinic instability. And here the forcing is wind stress. But again, there is an understanding that it's not just the change in radiative forcing that tells you the stratification, but the baroclinic instability can change as well. And indeed, people have run high resolution numerical simulations, and they find that those changes, even pushing numbers, might amount altogether to changes of just a few percent, once you account for the fact that as you increase the wind, there is a response that tends to equilibrate it. So things don't change all that much. So it's very difficult to change that slope, except if you massively change the winds and somehow you find a way to suppress baroclinic instability. So that change is probably very small. While the change in sea ice, when I said the 5 degrees, a change essentially of 25% in sea ice extent, that's a large change. So it's pretty clear that between the two, it's very easy to see that there was a change in sea ice line, but probably not as much of a change in slope. So that argument I've given you before is probably pretty robust. And indeed, you see numerical simulation like the CSM that I've shown you before. So again, this was the picture that I alluded at before. Then these are the two overturning circulation I described for the modern climate versus a glacial climate. And I'm trying to put together on top of it, this delta C13 reconstruction to show in what sense we are seeing something consistent with it. This picture is only for the Atlantic. So you see the water moving north, that would be your big plume of orange water coming south. And below it, there is a bit of this Antarctic bottom water coming in. You don't see necessarily, and that whole structure is below the 2,000 meters of, both this water and that water are able to penetrate below 2,000 meters, which is the height of these ridges and seamounts. When we go instead in the present day climate, in the glacial climate, the claim is that you have now this closed overturning, and now you see above that essentially all this water from the same source from the Southern Ocean now coming with the same signature, and they're all sitting below 2,000 meters or so, which is the height of ridges and seamounts. And you see indeed that blue shading is sitting pretty deep in the water column below 2,000 meters, and now you have much more uniform and extended column. So at least this rearrangement of water mass is not inconsistent with those patterns of delta C13. One can try to be even a bit more quantitative. There is another delta C13, maybe I never said it and I should have, and I apologize, is the ratio between two isotopes of carbon. It's carbon 13 and carbon 12. Carbon 12 is the dominant form of carbon, but there is a tiny fraction of carbon 13 in the Earth system, and that small fraction can be used. So the delta C13 is just a ratio of the two, and small changes in the two we'll discuss in a second way. They're mostly associated with biological processes and some fractionation between water and air. But here for the moment, we're just using it as a tag. But there is a second isotopic ratio you can use, which is delta C14. That's quite different. It's now the ratio from C14 to C12. C14 is even more rare. I mean, I think C13, I don't know, what is it like? Here, I'm not a chemist, so I apologize if I misquote, but it's something like 1% of the total. It's a pretty small percent of the total amount of carbon. C14 is even smaller than that by a long shot. And on top of it, it's an unstable ratio. C14 decays radioactively. C14 is generated in the atmosphere from cosmic rays and bombardment that transform, if I think, nitrogen in C14. And C14 itself has a lifetime of around 5,000 years, so sometimes it will decay away and you lose it from the water column. So that's quite useful because since you're generating the C14 and only in the air, by the time this carbon is taken up by the ocean, it just decays, it's not regenerated. So it can be used as a clock in a sense, because it just tells you the time since that carbon was last seen at the surface. And so now we can look at the profile of delta C13 in the Atlantic for, well, let's say the upper picture is definitely for the Atlantic, and the dotted lines are observations in the present day North Atlantic. And you see that the profile of delta C14, what we care mostly about is that it doesn't show, at least for the Atlantic, very large changes in its value below, well, definitely 2,000 meters, maybe even under 1,000 meters. And the understanding is that most of what you see is waters that come from two dense water sources. They come depth in the ocean, where especially the green line is what floods most of the North Atlantic. We've seen that green line really was spanning, was the orange component of delta C13, was spanning most of the water column. It's water that are not too old because they've been formed through convection on the surface and they flood most of the Atlantic. There is then a small source of dense water, the blue line that comes from Antarctica. You do see at the very bottom that there is a slight increase in ages. These water are a bit older, just because they are mixed a bit with Pacific waters and other waters that are older. So you see a slight signature, but they're not terribly different in age at that point. Now, I apologize for the title there, and it will become clear in a second why I called it Atlantic, but we can look instead at the Pacific picture. So the black dots are instead the profile for the present-day Pacific. And you see that the profile is very different. There is a bulge of very deep water in the middle of the water column. And why is that? Well, if you remember, the Pacific really looks always a bit like this. You have water at depth, and then rise towards the surface very slowly through mixing before they come back. Right? There is no upper water component. And so this dense water are this water that were coming as slightly younger water once they sank around Antarctica. By the time they come back, they're even more depleted in delta C14. They lost a lot of their delta C14, so their age is much longer. So now, what you see there is also a blue line in these two panels. And our claim is that these are solution of a delta C14 like tracer in a numerical simulation, which uses that circulation that you see there. So I just advected delta C14 with a simple model that reproduces that overturning circulation. This is a paper by Berkey et al. People want the specifics. And so the blue line is the prediction of that model for the profile of delta C14 now for the Atlantic Ocean. And we really want the Atlantic Ocean because that profile is for the Atlantic Ocean. And so you see that it correctly predicts the age distribution for the Atlantic. Now, that other blue line is instead the profile that we would predict in the North Atlantic for a glacial climate. Now, all of a sudden, also the North Atlantic should have this return flow, because now this circulation is not applying only to the Pacific, but also to the North Atlantic in a glacial climate. And so we predicted there is this bulge, much like we see today in the Pacific. So now the question is, do we see anything like that in the observational record? Why is it that at some point, close to the end of the lecture, I lose the upper screen? It happens every time, so there is something. In any case, then I'll have to look here because I don't see it there anymore. Here we are looking at vertical profile of delta C14 from 3 cores that were collected. You see the picture here at 3 different positions in the southern hemisphere of South Atlantic. This is that's Argentina, and this is South Africa. And so they're trying to look at the limb of the South Atlantic that I was describing, and you have 3 profiles. And on the left panel, we're looking at the delta C14 profile itself, which you see is pretty uniform in each one of the 3 profiles. They get to different depths depending on where they are in the water column. But you see that they are pretty uniform in the vertical. You can compare then those 3 color vertical profile into age, difference in age of water masses between the present and the LGM. Sorry, this is just, you're converting the vertical profile in an age of the water masses, which require subtracting, knowing what was the source value of delta C13 and what it is in the interior. But just to show you that, again, the age of water masses seems to be pretty independent of depth as a function of, well, independent of depth, so it doesn't change much with depth. So both the age and the delta C14 are pretty uniform. But then what they do at the 3 depth levels where they have profiles, where they could record the timing or the change in delta C14, they're showing you now the change between what the value became at the last glacial maximum. So you see that shallow in the water column and very deep, the change is pretty minor, but there is a big change in depletion in delta C14 at mid depths. So it's like those water, all of a sudden, compared to what they are today, they are much more depleted in delta C14. you can convert that in a change in age, and that would suggest again that the age change was pretty limited, very shallow in the water column and at very depth, very deep in the water column. But in this mid-depth range, instead, the age of water mass got older, just because delta C14 got depleted, so you're converting into an age. And that's consistent with the idea that what you're really seeing is this overturning circulation, making the water, this new overturning circulation that returns water through diffusion in a closed loop in the deep ocean. So this water becomes very old because they are never really actually ventilated from new water from the surface. And well, I guess I can even stop here, but then let's first review what we, at least we suggested, that sea ice around Antarctica. The main point for us is that we really think that sea ice on Antarctica expanded the LGM in response to colder temperature. That seems very likely. Then we made the statement that sea ice expansion split the present day single cell overturning circulation. And what I mean by single cell is that one cell that spans both oceans in two separate cells stacked on top of each other. Now the claim is that what is the impact on the carbon budget of the ocean of this rearrangement is that this deep water now are outcropping only under sea ice. So dense water, so deep waters in the ocean are very rich in carbon. When they come to the surface, particularly in the Southern Ocean, they can degas and lose all that carbon. But now you're putting a lid. So all of a sudden that carbon can just accumulate depth. The only way that carbon will eventually be diffused or return to the surface in equilibrium is this through very small diffusion. And it's very small because this deep cell is all confined to within, it expands all the way to the top of rigid and seamount. So above it, mixing is very weak. So you're going to get a very strong gradient with large carbon stored in the abyss, much less carbon above. And then the next part that we could get into that we are working on now is that these results now are supported of the claim that there is indeed a big storage of carbon, of in particular biological carbon or biologically mediated carbon, respired carbon in the abyss, is supported by this delta C13 profile that I've shown you before, if we actually look at what sets the delta C13 profile. Maybe what should we do? We can stop. I can take questions, and people want to stay over. I can go a bit through the delta